So far when we've looked at factoring, we have focused entirely on quadratic polynomials, meaning they've had an x squared in them and not anything higher than that. We've looked at sum and difference of cubes, so there was a couple of examples of cubics. But we can use, it turns out, those same strategies that we've been using for quadratics to factor higher degree polynomials when they're sort of quadratics in disguise, is the way that we want to think about it. So we know how to work with perfect squares and we know how to work with perfect cubes. So because of the way that our properties of exponents work, if you have a power, say x to the 8th, that is divisible by 2, then that means that those represent perfect squares. Because remember, when we do a power of a power, let's kind of think about this backwards first. Like right here, if I took x to the 4th and raised it to the 2nd power, the rule is to multiply those exponents. So we would get x to the 8th. Well, if I wanted to kind of unsquare x to the 8th, we would do that in reverse. So I would divide by 2. So that's how I figure out what that is that's being squared. So anytime you see an even exponent, that means it's divisible by 2, and that means that it's really a perfect square kind of in disguise. Okay? Now, if you have an exponent that's divisible by 3, using that same logic, those are going to be perfect cubes. So, for example, x to the 6th, that is x squared cubed. And again, 2 times 3 would give us 6. X to the 15th is x to the 5th cubed. So we can kind of break them down. To figure out what we cubed, you just divide the exponent by 3. Now, x to the 6th could also be written as a perfect square if we wanted to. It just depends on what we need. So x to the 6th is also the same as saying, x to the 6th is also the same as saying x to the 3rd squared. And in this case, we'd be looking at a perfect square. It just depends on what we need and what we're trying to factor. So there are going to be some numbers that are both divisible by 2 and by 3. And so you just got to kind of think about the situation and what it is that you're working on. Alrighty. So let's look at some examples of factoring where we have to kind of take this into account. So we have a couple of different tricks up our sleeve. So we want to be looking for polynomials in one of these 3 forms, okay? So the first one is quadratic form. Remember, we said the standard form for a quadratic expression looks like this. We use our A, B, and C to set up our diamond, factor by grouping, and so on and so on. So we need something like that. We need maybe a difference of 2 squares, a squared minus b squared, or we need maybe a sum or a difference of cubes. It doesn't matter which, you can do both of them. With a difference of squares, it's only a difference. There is no sum of squares. So if it's a plus perfect squares problem, it's not factorable. But those are the 3 things that we're kind of looking for. So if you look at number 1, that looks like it might follow the form of the first one, ax squared plus bx plus c. Except they're not x squareds. The middle one is, but the first one is not. So I need to see if x to the 4th could be rewritten as something squared. And it can, because that is even. The 4th power is even. That means that this is the same as saying x squared squared. Okay? So what I like to do in order to make this problem a little bit easier is replace that variable with something else. Let's say that I'm going to use u instead. So I'm going to use u to stand for x squared. Since that's x squared squared, that means I can really write this as u squared minus, here's another x squared, so I can make that 3u, and then minus 10. Now that looks like this first form right here that we want. And so that is something that we know how to factor. And if you go through the factoring process, which I'm not going to spend a lot of time on now because we've talked about it a lot, but this will come out to be u minus 5 times u plus 2. However, remember that u was not what we originally started with. We were just using u to hold the place of x squared. And so now that means to make my final answer, I need to put the x squareds back where the u was. And so we get factors that look like this. Now you want to take a peek at each of those factors and see if they're factorable anymore. So I see that I have perfect squares here. X squared is a perfect square, but 5 is not, so that doesn't do us any good. And this one here has a plus, so that doesn't do us any good. So that's how I know that I am done factoring. Okay, so let's look at number 2, 9x to the 6th minus 25. Now, 9x to the 6th minus 25, I see that I have two terms. So that kind of tells me that I want to be looking at one of these two. And I see that I have subtraction. Well, either one of those can be subtraction, so that's still on the table. So I need to try and decide, can I write that as perfect squares or can I write that as perfect cubes? And you just got to kind of check. Look at the numbers you've got. We don't have perfect cubes here. 9's not a perfect cube, 25's not a perfect cube. But they are perfect squares, okay? X to the 6th is x to the 3rd squared. So again, let's take out that x to the 3rd and call it something a little bit nicer. That makes this now 9u squared minus 25. And that we know what to do with. We can factor that and we'll get 3u plus 5 and 3u minus 5. If you need a review on factoring, see some of the previous videos posted. But now, to finish this out, we need to put the u back in where it came from, so that means 3x to the 3rd plus 5 and 3x to the 3rd minus 5. Great. And looking at those, there's no GCFs, there's nothing else that we can factor there, so that's all that we can do. Okay, the last one here, x to the 9th plus 27y to the 3rd. So again, I see two terms, so I'm looking at the last two. But since that's a plus, the only one that's allowed to be plus is my sum of cubes. So I'm hoping that those are going to be cubes. Now, they do end up being cubes because, well, the y cubed is obviously a cubed. But the x to the 9th, 9 is divisible by 3. This is x to the 3rd cubed. So if we take out the ugly piece there and let u be x to the 3rd, then that means we have u to the 3rd plus 27y to the 3rd. And if I look at what I have, this means that u is a and 3y is what we're cubing there. So again, we build our formula. A squared, ab, b squared. We went over this formula in a previous video. And now we use SOAP. So this is a plus. So the same sign, opposite sign, always positive. SOAP. Same, opposite, always positive. So now we just plug those into our formula. So we have, let me switch this here. We have u plus 3y times u squared minus 3uy plus 9y squared. But remember that u was holding the place of that extra messy stuff we had, which was an x to the 3rd. So really what we have now is x to the 3rd plus 3y times x to the 3rd squared minus 3x to the 3rd y plus 9y squared, and we can finish that out by fixing this exponent here, and that gives us a final answer of this, x cubed plus 3y times x to the 6th minus 3x cubed y plus 9y squared. Okay. So that really allows us to kind of factor polynomials that we weren't probably able to before without kind of knowing that those were in disguise. Now, if you can factor without putting the u's in there, if that makes sense to you and you want to skip that step, go ahead. But I find when we're just getting started that it's helpful to kind of simplify the problem a little bit here. So what we want to be careful about is that we make sure we get everything. So make sure that you always start by checking for a GCF. None of the problems we did before had one, but some of these might. And like I've mentioned before, you always want to check your factors to see if you can factor them any further than what you have done. So number 4, hopefully you recognize that those are 2 perfect squares. I know that x to the 4th is a perfect square because 4 is even. That means that I have x squared squared minus 1 squared. 1 is a perfect everything. It's a perfect cube, square, 4th, 8th, whatever. So that means that this is A and this is B. And so we can factor that using our difference of squares pattern. X squared plus 1 and x squared minus 1. We went over this in class. Okay, so we have that. And now I want to look at what I have left. This one is done. X squared is a perfect square and 1 is a perfect square, but since it's a plus, we can't do anything else. But this one is another difference of squares. Here I'm squaring x and here I'm squaring 1. So if you left it like it is in the purple, that would not be correct because when we factor completely, we need to make sure that everything that can be factored has been factored. And so this is what we get when we factor this last guy here. This would be the final correct answer for that problem. You always want to make sure that you expand things further if you can. And this was a difference of squares. So when we factor that, it breaks down even further. Looking at number 5, I noticed first that there is a greatest common factor. So I'm going to start by factoring out an x. That gives me x to the 4th minus 6x squared minus 27. And you may notice there that x to the 4th is even. If I divide it by 2, I get x squared. So when I divide that by 2, that means that I have u squared, because squared is what I have left when I divide by 2. And then x squared, that is what u would represent. And then minus 27. So if we are letting u equal x squared, this is what we end up with. So that is going to factor to, let's see, u minus 9 and u plus 3. And now let's put that all back together. So we have x, our GCF from the beginning. And then if I take my u's back out, I have x squared minus 9 and x squared plus 3. And when I do a quick scan of this, I notice that this guy is another difference of squares. A squared minus b squared. Now, I'll be honest, that was the day that a lot of you guys left class early instead of waiting to hear the last little bit there. So you may want to do some research online and read the section in the book where we went over difference of squares because as you can see, this is kind of an important thing. So that is going to factor to finish out all the way. We have x. X squared minus 9 becomes x plus 3, x minus 3. And then x squared plus 3, that can't be factored. So this is the final answer. Okay. So the last thing here is just kind of a summary of all of the different factoring techniques that we've looked at. Okay. So these are the 3 steps that you always want to go through when you're coming across a factoring problem. So 1, you want to look for a greatest common factor. And then the second thing you want to look at is how many terms it has. Make sure that you're looking for powers that might be in disguise. You're looking for squares and cubes that might be in disguise. So if it has 2 terms, you want to see if it's a difference of squares or a sum or difference of cubes. It's got to be one of those formulas. If it's not, then it's not factorable. If it has 3 terms, then you want to use the diamond problem and grouping. That's what the book calls the AC method. And if you were there when we talked about the A equals 1 shortcut, you can go for that. And then if it has 4 terms, it's already set up to just go straight to factor by grouping. You don't have to do the diamond problem. It's already set up to group. And then lastly, make sure that once you've factored that you look at all the factors you have to see if any of them could be factored again. So here is a set of problems that you can try. I'm going to put the answers up here in just a moment. So I would suggest that you pause the video and try these on your own as a good study guide, and then you can come back and check the answers after you've worked them out. So here come the answers. And here's all the answers with all of the work. So take a look through these, kind of see if you can figure out where you're making some errors. And if you have questions, please send me emails and we can try to sort you out.